Good evening, all.
Good evening, madam.
Good evening, madam.
Good evening.
Dr. Tarkeshwar, how are you, sir? We are very happy you have joined this program.
Thank
My
you.
MC, thank you. MC team, can you please start the program?
Yes, we are ready to start the program.
Yes, sir. Please wait for a moment so that the MC team will give a chief guest intro and we'll start the program formally.
Yes, sure.
So, MC team, please start the program.
Pleasure to welcome you all to the Day 3 of our Faculty Development Program, organized by the Internal Quality Assurance Cell and the School of Computing, BT Institute of Arts and Science. Today's session focuses on the fascinating and highly relevant topics deep learning techniques optimization. Deep learning is a part of artificial intelligence that enables computers to learn from data much like how humans learn from experience. It powers many technologies we use every day such as face recognition, voice assistance, language translation, and even self driving vehicles. To make these systems work effectively, we need to train them well, and this is where optimization techniques come in. These are smart methods that help deep learning models learn faster, become more accurate, and perform better. In this session, we'll get a clear and simple understanding of how these techniques works and why they are so important in today's all AI driving world. We are delighted to have Dr. Takeshwar sir with us, who will guide us through this insightful topic with us with his expertise and experience.
I would like to welcome A. Kanishka from second BSc CSA to deliver welcome address.
Good evening, everyone present here. It is my great honor and privilege to introduce our esteemed chief guest for today's faculty development program, Dr. Takeshwar sir, a distinguished academic and a research in the field of computer science and artificial intelligence. Dr. Takeshwar currently serves as a professor at Roorkee Institute of Technology, located in the picturesque city of Roorkee, Uttarakhand. With a rich academic and research background, he has made a significant contribution to the field, particularly in deep learning and its optimization techniques, which is also the central theme of today's session. A respected name in academic, Dr. Takeshwar has guided numerous research scholars, published extensively in reputed journals, and actively participated in national and international conferences. His deep insights and passion for technology make him an invaluable research and inspiration for aspiring educators and professionals alike. We are truly privileged to have Takeshwar sir.
So you can take over the session, sir.
Yeah, thank you, madam. So, dear faculty members, today we are going to discuss about deep learning techniques to optimize our models in training models based upon the neural network, how we can optimize. So now question arise, what is optimization? Optimization means something is already there, but how we can do this in much better way so that we can improve the accuracy and we can minimize the loss. So that is called optimization. So in this FDP, we are going to discuss about optimization and what are the basic steps, what are the algorithms we are using to optimize our models. So the very popular model is gradient descent. The very popular one is gradient descent, and how to optimize it and challenging what are the challenges we face in the industry or in the academic. So let's proceed. So this is the architecture we follows. One side we are providing data and we are training our model, and soon we realize the accuracy of the model is sometimes increasing, decreasing. So many things are happens, but it is not always perfect. So it is, anyway we can say all models are cannot be perfect, but still we can reach closer to the accuracy so that we can minimize the computation and we can improve the accuracy. That is our target. That is why we do optimization. So it method improves the model performance by minimizing error, accelerating training, and enhancing generalization. So what type of optimization techniques we have in this? So very popular techniques we have, four techniques. First one is gradient descent based optimizer. Those are structured gradient descent, ADAM, and SM props. Hyperparameter tuning also we can use, their learning rate, batch size, and dropout rate. And architecture optimizations like layer depth, neuron count, and regularization techniques. So these things we use in optimization. So step by step we'll discuss each and everything. So why it is important? What, why, how it will improve before our normalization and after normalization? If we normalize, normalization process decreasing the computation. So earlier you were taking a time around 1 hour to train our model, but after normalization it will reduce around 45 minutes, 40 something, it can be decreased. So we have tested optimization algorithms, optimization techniques in different applying different algorithms along with normalization. So as you can see here, we have tested with RMS prop, Adam, and same RMS prop with Adam with normalization, without normalization. So you can see the top one is best models, and you can say that is a better approach. So that, so what are the major techniques we applies in this? And I will show you some code as well. So how this technique works. So if you optimization, those participants from the Python coming from, they they can use this code optimizer. So we'll discuss all these methods right now, and I will be sharing this code with you as well just after this FDP, how the comparison between the all these models and the techniques, which one is better in what type of application. So these all things I'll discuss. So now coming to the slide. So in this, the effective of choosing the optimizer algorithm to improve the computer vision. So it is not about everywhere you can apply the same. In computer vision, we apply the different uh, techniques. So this study compare momentum, gradient descent momentum, ADA grad, ADA delta, RMS props, Adams, and a- NAG. So this optimization technique we can use in different aspects or different applications. So the very popular one is hyperparameter tuning. In hyperparameter tuning, you might have noticed uh, two things are there here: grid search and random search. And this random search and grid search we have studied in the data structure part. Same approach we have implemented as it is in the AI models. So in this, we are trying to minimize the computation, and directly we are reaching to the particular target that we are going to achieve. And another technique we use is here Bayesian optimization, and best practice is learning rate and scheduling batch normalization. So let's dive deeper into this. So we have a data set. We have data set we have split it 30 by 75, 25, 70. So like this, we percentage wise we have split our data for testing and training data. So this is what we have mentioned here: split data set into testing and training, and we have stored in different warehouse, or you can say storage center. So master data is stored here, training data is stored here, and test data is stored here, different locations. Or you can consider, for small data set, these are folders. If you are going with a big warehouse, then there can be some cluster. All right, then this data set, we are taking training data to the training model, and model is getting trained. And once it is done, then we have to test this. So the testing data we are passing to the model, and if everything is okay, then it is fine. If not okay, then we are trying to tuning, hyperparameter tuning. So this is how your performance of your model can improve, or you can say we can optimize the actualization or particular accuracy. So hyperparameter plays very important role in the unlocking the full potential of deep learning models by enhancing accuracy, stability, and training efficiency. So basic techniques are preventing overfitting, preventing overfitting. So overfitting means we are our model is performing in testing is okay, but in the final testing in the production it's not working well. So or else we can use L1 L2 regularization, dropout, early stopping, and data augmentation. So right now we will discuss everything by hands on, or if time will not allow me to complete this, then I will share the slide and code as well, so that you can execute by yourself. All right. All right, so now we have a depth versus width neural network. Activation functions, we can use ReLU, Lecky, and ReLU, CNN, RN transformation tuning. Optimization transfers, learning pre-trained models, like fine tuning versus feature extraction, benefits of data, limited data, and use of image text signal domains. So now I'm coming to the, and in the beginning itself I told, we have discussed how we are going to train our model and how we are going to evaluate, how we can know whether this is up to the mark or not. So first and very important thing is accuracy. We are going to evaluate. uh, we can find with the help of a confusion matrix. We can use this confusion matrix. And precision, how these precisely application is working. F call, F rescore, recall, confusion matrix, ROC, AOC curve. So this is how we need to plot accuracy or confusion matrix. Based upon the confusion matrix, how many true positive, true negative are there, and true false, true negative. So true false means those are accurately classified as a positive, so that means it's accurate one, correct one. But something was false but positively they created, but something was negative but it they find as a positive, so we can classify true negative. And for something was positive but it find as a negative, so we can draw some confusion matrix. Based upon that we can calculate accuracy, specificity, precision, and recall. So now, what are the formula to this? True positive, TP stands for true positive, true negative, and true positive, true negative plus false positive plus false negative. And specificity, we have a true negative plus false positive. Precision, true positive upon uh, true positive plus false positive. Recall, we can write true positive upon true positive plus false negative. So this performance matrix, we can calculate accuracy, specificity, precision, and recall. So in this, so now just now we have discussed few terminologies we have used in the we use in the artificial intelligence deep learning. Now coming to the little deeper dive. Optimization is an act of making something as fully functional and perfect. So with the here we are going to use mathematical approach. So it's a group of we can say it's a group of mathematical principles and methods used for solving quantitative problems in many disciplines. And disciplines can be anyone. Whatever techniques I'm telling you, this can be applied either in the physics, biology, engineering, economics, and business. Anywhere we can apply. So these are general techniques. So with the help of this, we can minimize and maximize the results or minimize the loss, so that we can achieve our targets. So deep learning is basically based upon the expressibility, optimization, and generalization. If we can cover these 3 points, then we can achieve to the deep learning, best deep learning fine-tuned model. So what else is needed? So expressibility, in the sense we can say what neural network you are trying to get it done. So how efficient is the one neural network connecting to another term of set of functions they can represent? What inductive basis exists in modern neural network? Once you have trained your model, it times to go with optimization. optimization, how we can find the best weight. Obviously, it is based upon the weight and bias, right? So weight is a randomly assigned some number. So how we can assign the best weight to fine tune our model so that neural network for given task. So we can guarantee to find the best one. So that is called optimization. In the optimization, we are going to achieve this. How we can do it for, and generalization means why does solution in training set generalize well to an unseen test set? We can bound the generalization error. So why it is important? Where it fit? So the difference is average instance rate changes according to the graph. So you can see initially optimization is always there. In 1970s, we have a computers were very slow, and we try to minimize the error, improve the speed with low cost. Earlier computers were busy, very costly. Now it is very cheap, and we are getting high amount of computation. So that same thing we are trying to achieve in the optimization. So means our target is to achieve the best one. So where we can use this optimization? Optimization we can use to identify the brain cancer, magnetic resonance imaging, or we call it MRI, to find particular uh, particular type of disease to we can detect. And images produced by magnetic resonance, you can see here brain, especially in brain tumor or cancer, prostate cancer, lung cancer. So in these cases, we can it can be very helpful optimization. And on the left hand side you can see in robotics as well. In robotics, sometimes robots makes a mistake. So why it has happened? Because it is not able to calculate uh, action properly. So that's why if we can integrate optimization techniques, then it can perform better. So I will show you these programs as well. Next, optimization we can use in network, like IP addresses recognition, and we can find the shortest path on the network. Right now, many participants are connected across the globe, and they are getting me on real time, and does not matter which part of the world you are sitting. It is only happened because of the routing. So routers are sit on the network and they check what is the shortest path. OSPF protocol we uses here to check the shortest path to transport the data in shortest manner. So to improve the performance. Next, why automation is crucial in deep learning? Because the loss function evaluates a model effectiveness by computing the difference between expected and actual output. So usually it happens if I'm saying a 2 plus 2 makes it 4. What if it is saying 3.9? What if 4.1? So it is closer to 4, but it is not accurate. So something is different. So so we are targeting whatever the difference coming between the expected output and actual output. So the common loss functions we uses here includes a loss, log loss, hinge loss, and mean square loss. Or in other words, we can say error. So optimizers we can use based upon the weight, bias, weight and bias, and minimize the loss function. So like RMS props, Adam, SGD, stochastic gradient descent. So what is the formula to achieve this? So this is a mathematical formula. We have theta k plus 1 theta k minus alpha jq. So here we have updated parameter vector at position k plus 1. K is a position and theta k is the current parameter vector at the kth position. And alpha is the learning rate. What is the learning rate? Uh, which is positive always, and scalar that determine the step size for each iteration. And this is the gradient's cost function. So what are the initial steps? First, you need to initialize the parameter. Participants, if you are not speaking anything, so please mute your mic. So first steps takes initialize parameters. So in the initializing parameter, we randomly initialize the model parameter, and then we calculate the gradient. So gradient is something like it looks like a cone, upside down cone and upside cone. Dear participants, please mute your mic. So initially, so these steps we can initialize the parameters for models. Then we can calculate the gradient. Gradient is nothing but a slope. It's a slope between the top and most and lower most value. Then base to minimize this, we so this is the one I'm talking about. So this one I'm talking about. This is the topmost and this is the belowmost lower. So this we need to update the parameters to minimize this one, the gap. So adjust the parameter by moving the opposite side direction of gradient scaled by the learning rate. So this is how we can improve the performance of our app, model. So basically, what are the challenges we face into this, and what are the techniques we apply in this? So usually we apply the techniques called non-convexity, exploding gradient or vanishing gradient, and saddle point. So these are the called saddle point. The you can see the curved one on the top, on the bottom side. These are called saddle points. And we need our target is to minimize the distance between the top and bottom side. So that is our target. So this is how we are going to improve the performance. And that, so what are the challenges we face in this? We usually face problem with underfitting and our overfitting problem is affecting the deep learning models. Other, data quality. If, as we say in the industry, if you input the garbage, you will get the garbage. So that's why data quality, to tune in or to sanitize the data or to clean data and quantity, you need to provide the specific amount of data. If you are providing more data, means you are very closer to the accuracy. So that's why you need to provide as much as possible data. Computational resources, you require high amount of computation. Anyway, you can train our model on your laptop as well, but laptop will require more time to complete or train our models. So that is why Google Colab is very good platform where you can execute these code, and these code I will share with you so you can execute by yourself. And whatever images, optimization images I have used in the slide, everything you can find there. So next one, interpretability, hyperparameter tuning, and scalability, ethical bias issues, hardware limitations, and adversarial attack. So these all we are going to discuss. So let's first discuss the terminologies. What are the terminologies? Oval part, top side or bottom side. Part is known as schedule. Schedule, a global minimum, is the global minimum point whose gradient is zero, but not local minimum. So this is a local maximum and minimum, global minimum and local minimum. So local minimum is actually local minimum point whose gradient is zero. So this gradient becomes in this point becomes zero, whose gradient is zero, but not global minimum. So schedule point is the context of function. So this schedule point is the context of function of the two or more variables is a point on the graph where the function does not exhibit a local maximum and minimum, but instead of slope changes direction. So this is the slope. So you can see it is going from top to down. So this our target is to minimize this slope. Okay, so at the saddle point, the function may increase in the one direction while decreasing the another, giving the surface a shape similar to the schedule. So you can see this. So this is the global maxima. So the global maxima, and this is a local maxima. And one moment. Yes. So now let's. So this is global maximum and this is local maximum. So, and this is global maximum, and or in a layman language, you can say this is the smallest one and this is the biggest one. And if you want to learn more about this link I will share with you just after this. This is a source where I have collected this information. I'm sharing parallelly. If any terminology you are not able to get, you can understand from here, or you may ask me questions just after this call. Now, what are the challenges we face in the deep learning optimization? So, challenges is especially loss function for linear regression is the mean squared error. In the linear regression, we all faculty member might have faced this issue, mean squared error. So, which is always convex. So this means there is only one single optimal minimum, which is global maximum in the entire mean squared error function. And we do not need to worry about the existence of local optima. So let's dive into the deeper into this. So if you see in this, we have trained different models and we have these findings. So if a small learning rate, then you can see the curve is sloping to the right hand side. So a small learning rate require many update again and again before reaching to the maximum point. So you can see step by step, you can see maximum updates are needed again and again. If we have a just right accurate data, means directly we are reaching to the particular point. The optimal learning rate shift reaches with the maximum points. If data is too high, if it's too high for learning rate causes drastic update, so which lead to the divergent behavior. So these are the problem we faces while we train our model. So which one is the best approach? So choosing the right hyperparameter is one of the crucial step for optimization. The learning rate is such a parameter that influence the conversion rate. If we choose too small training rate, it would require many updates before reaching to the optimum. And if we choose high, then it leads to the divergence. So this is a problem. So we need to reach to the accurate one, exact one. So that's the problem. So now new term comes into the picture called local optima. So if we are in the local optima, then we can say among the global maximum optimum may be less critical because solution may be sensitive to the noise, and local optimum may still yield satisfactory results, right? So let's dive little deeper into the same graph. So the point, this point is known as plateau. So this point is known as plateau. This point is known as plateau. So this region on the loss surface where gradient of loss function becomes very small and nearly flat. So you can see it's a nearly flat. So there is no difference into this. So the loss function is very slow, very shallow slope. So you can say consider just like a straight line in multiple dimensions. So making it difficult for optimization algorithm to make significant progress towards the minimum. So when the gradient are close to zero, the optimization process slow down and it may takes a long time to converge to the optimal solution. So plateau are the particularly problematic in deep learning. So plateau is a problematic because neural network can have a large number of parameters and its likelihood of encountering flat regions increases with the model complexity. So now reach to the another terminology called saddle point. So you can see the highest point and lowest point. So highest point known as saddle. So saddle point, these are known as saddle point. So critical points in the loss surface where the gradient is zero and the surface is relatively flat. So this surface is relatively flat in some directions and steep in the another one. So this is not an extremum. Extremum means neither minimum or not maximum. So the comparison between the two, you can see in the graph on left hand side sigmoid versus derivative sigmoid, or you can see vanishing gradient comparison you can see. Now final optimization results, how the results looks like. As you can compare these images, optimization in the case of well condition versus ill conditions. So you can see in the well conditions, it directly reaching to the ill condition, it's taking time. But if it is healthy condition or well condition, in it is using less amount of computation. That is our target. So how it is affecting? So these models, when we train, and the where you will see the loss. So you can see we have highlighted the loss. Earlier it was loss 0.9050, but now it is 0.8906, and then next iteration it is decreasing, one increasing, right? So this is the difference we are getting, right? So if you are going to use smaller learning rate, then so much local minima and global minima you will see in this. If you have a large learning rate, then you will see the long gap between the starting point and end point. So this approach we are going to use in the economics, one term called, this term is coming from economics actually. Non-convexity refers to the violation of the convexity assumption of elementary economics. A non-convex function is wavy and has some valley or local minima, are not deep as well as the overall deepest valley, known as global minima. So this one we have already discussed. Next one is convex functions. What is convex function? You can see the graph itself represents convex. So that's why we call it convex function. So convex functions are particularly important because they have a unique global minima. Unique global minima means at certain point they are touching to the particular slope. So if we want to optimize the convex function, we can be sure that we will always find the best solution by searching the minimum value of function and maximum value. So this is the minimum value, or this is the maximum value. So as you can see in the graph, and mathematical formula you can see on the top. All right, now next we are moving towards next. So common convex functions are like L2 loss, log loss, L1 regularization, L2 regularization function we can use. Common convex functions we can use. Non-convex functions, like where we find always in the straight line, we are getting the results following straight lines. Is a function is said to be non-convex if it is not convex. So geometrically we can say non-convex function is the one of that convex downwards has multiple peaks and valleys, multiple peaks and valleys, and it is two-dimensional. So the challenges with the non-convex functions is that they can have multiple local minima, which are points where the function has lower value than all neighboring points. That means if we try to optimize a non-convex function, we may get stuck in local minima and miss the global minimum. So, all right. So let's see the difference between convex objective and non-convex objective, convex constraint and convex constraint. Right? You can see this one is convex objective and convex constraint. So this is a convex objective, this is a convex constraint. And on the right hand side, you can see non-convex objective and non-convex constraint on the bottom side, you can see. So this is a difference. All right. So obviously you can see this is the best or easier to optimize our model. That's the best approach. Now coming to the minima and maximum functions, how they works. So minimum maximum functions refer to the highest and lowest point. So in the graph, you can see which is the highest point and which is the lowest point. So you can see this is the lowest point, this is another lowest point, this is another point. So P1, P2, P3. So P1 is a local minimum, P2 is a schedule point, and P3 is global minimum. So this is the graph we calculate. Next. So how the loss minimization works in optimization techniques. So we have a technique. So what model is expected and what we are getting. So the difference between the what we are expecting, what we see. So known as loss. So the loss of the machine learning model is calculated with the help of loss function. So how the loss can be minimized. So and so you can see this is a cost. Cost is slowly is decreasing. Slowly is decreasing. So that is called with the optimization function we are trying to reduce and we are taking to the minimum. It is not 100% accurate, but it is trying to minimum. Let's proceed to vanishing. This is also very popular approach to work with gradient, vanishing gradient or exploding gradient. So what happens? You are trying to tune in, but sometimes it happens that it is over tuned. So because of that, it starts giving false results. So this is known as evil twin of vanishing gradient. Gradient is good, but vanishing gradient sometimes creates some problem. So it in instead of gradient shrinking, it blow up and leading to the massive weight update that throws the model parameter out of whack. So you can see in the image as well. So without gradient or with gradient clipping, uh, gradient clipping is a technique to avoid gradient explode. So during the model training, this architecture input layer and hidden layers are there, and finally we are getting the output. And at the end, we have applied a token and to check whether condition whether it is up to the mark or not. If not, we will retrain it. So feed forward network we have used here. If it is not trained, then we can go error back propagation. So this is a formula. We can go back propagation error, and again we will update the weight uh, to achieve the best results. Now, uh, exploring how to overcome this problem from this problem. So the first thing is gradient clipping. As you can see, we can see many images, and we have cut the topmost part, and which is the best part. So whatever the best part is, we have uh, uh, clip. So this is called clipping. So by setting the threshold, whatever the best threshold, we prevent the gradient from the exceeding the value. So we don't want to allow the more than that. So we can trim. So this clips the gradient to stop from the going wild. So we do not allow to go more than that. This is optimization technique. Smaller learning rate. So do not smaller learning rate will always ensure the best results. Reducing the learning rate help to slow down updates and ensuring the weight do not get out of hand. And another technique is batch normalization. In the batch normalization, we input the each layer and maintain the standard scale and prevent excessive large gradient during the back propagation. So it is just like everything in modernization. So for gradient clipping, we uses this mathematical formula. Okay, so 1 upon n start from the n equal to 1 and it goes to up to n, and we can apply this formula. And no need to write this formula. By default, these functions are available already in scikit-learn itself, scikit-learn or any TensorFlow or any AP. framework we can use. By default it's there. So just we need to call this technique a function. So gradient clipping is the process that helps maintain uh, nu- numerical standability by preventing the gradient from growing too large. So it is known as pruning. So when training a neural network, the loss gradient are computed through the backpropagation. So let's proceed towards few more optimization technique, or you can say gradient descent. It's what type of gradients are available. So very basic and very important one, batch gradient, s- stochastic gradient descent, mini batch gradient descent, momentum, and adaptive learning rate. So these all we can execute and we can find these type of results. So you can see the comparison between both of them. So you can see this batch starts and it goes to the particular place, and so the batch and mini batch taking time. Okay, so you can see the best, which is the best one. So green one is the best. And if you talk about sgd means we have a top point A, B, and C. So we need to minimize the slope distance between A to C. That is, so these methods will help us to achieve this. All right. So this is the results we find, and let me execute this code for you. So this is the, so we have non-convex function we have here, and this is a non-convex function derivative. So all function I have written, just we need to pass and execute, and we will see this type of results. So we can run this. Time is not allowing me. So we can see the comparison. Non-convex function. So this is a non-convex function, and this starts from the 2.5 gradient descent path 1, and it here from here it start and here it ends. So you can read this, right? So now you can close this. And another function is, so schedule points. What are the schedule points? So this is the schedule points. So the topmost is the schedule point. 0 point comma 0 is the schedule point. And how to find the schedule point? Function x comma y equal to x square minus y square. This is a formula to calculate the schedule. Now, if you compare between other, and if you see the gradient descent path on schedule point contour, so gradient descent path, this is a contour, and you can imagine on the one bed sheet you are trying to put some ball, and it will always try to reach on the center. So that is our target. So schedule point is 0 comma 0, and our target is to reach up to 0 comma 0 and start from the certain point x and y. All right. Similarly, another optimization technique we have, I will share just after this. Another one, this is a comparison between optimization path, start point, global. So a straight line we have drawn. So that this is the results we are getting if we are going to use technique ADA-grad. ADA-grad technique if we are using. This is what the optimization things we get it. And you here you can see uh, RMS props. So parameter 1 and parameter 2 we have tried to train. And star is a global maxima. So this is a global maxima, and this is starting point. Another one is, this is optimal path. So you can read the code I will share just after this call. Next, Adam. If you use Adam, so Adam also very popular. So that's why I'm telling you, I'm in my case as well. I'm using all maximum time Adam. I'm using optimization technique. And Adam, just one step ahead of Adam, we have an Adam. So here you will see less amount of computation to find this, right? Next. So all type of optimization techniques I have applied here and in different scenarios, how they behaves. Another one is regularization, and we have a regularization or regularization technique we have implemented here. Regularization techniques. So initially it takes time to run. So you can compare between with regularization or without regularization. You can see without regularization, you have seen it starts from zero and it takes time. And but on the other hand, if you regularize them L1, L2 parameters, then amount is computation is less used and comparing to previous one. So that is why it is very useful. So you can see the graph. So you can see this now. So this is a chart with noise. Even after injecting noise,
Excuse me,
still
sir.
yes.
Sorry for the interruption. I request all the participants to turn on the camera.
Dear participants, please turn on your camera.
Most of them have not enabled your camera.
Dear participant, please turn on your camera. Dear participant, please turn on your camera.
Thank you, sir.
Thank you, madam. So now coming back to after optimization, if we inject noise, still we are getting the almost uh, correct results. So that is the power of optimization. Almost correct result we are getting. Now next we are moving another optimization technique we use is ant colony optimization. Ant colony, if you go with, if you see the ant colony, so one ant find their food and they release some chemicals. So with the help of this chemical, all other ants can follow it, and even the other ant also keep on releasing the chemicals to find path. So after certain period of time, that path becomes very strong, so there is no chance of losing uh, uh, losing the path. So the same theory we are using in the optimization technique. So let me execute this. So it's getting trained. You can see here. So this ant theory we are using, uh, where even this theory is used by the Google Map to reach. It is helping us to reach on the particular point within less minimum time, and always you will get the numbers, and always try to get the shortest pass first. So that on theory we use it. So time is not permitting me to, and how the conversions of the on theory. So immediately you can see as we start training the model, and very quickly and very less number of iterations we are finding our task, and after that there is no very less we are reaching to the threshold. So we can minimize the error just after few iterations only. Next one is optimization technique called swarm optimization, uh, swarm, they find the food in local where they sit in the water, and after once it is finished they are try to find the next target, and they fly in the v shape, and once they reach then they start finding the food. So local search, global search technique we are using here. So this code as well I will share with you. So let's see how the effective it is. So on theory, earlier it was more than 20 iteration, and swarm optimization is very effective even within the less, within the 10 iteration itself. So you can say it is a better approach in comparing to ant theory. So anyone we can approach we can use, but which one is best in according to your model we can apply. So this is the results we are getting, and we immediately we are reaching to the conclusion. So the best global and true maximum. So this we are reaching to the target just after the few iterations only. So that's the best way. All right. So time is not permitting to go. So these all algorithm we have discussed: adaptive learning rate methods. So ADA grad, RMS prop, ADA delta, Adam, and Adam, and Adam W. So this is based weight optimization. Okay, so these all graphs we have seen. So this regularization techniques, we can use L1, L2 techniques, dropout, how it works. So these all things we have seen. So these all charts we have seen by code. So time also not permitting me, I'm going little fast. So now few questions I have. So please try to answer this. Which of the following is the primary goal of optimization in deep learning? So what is the primary goal? So basically to minimize the loss and improving the model generalization. So answer is B. B is the right answer. Next, which optimization algorithm is known for optimizing, adapting the learning rate for each parameter based on the historic sum of squared gradient? So obviously AdaGrad. So answer is AdaGrad. I will share the slide as well with you just after this. What is the common drawback of very large learning rate? So the oscillation ground and overshooting the minimum. So this is a problem when we go with large learning rate. So this is a problem. So which of the following technique helps to prevent overfitting and by random setting a fraction of neuron outputs to zero during training? So obviously dropout, correct? What is the purpose of momentum in the optimization algorithm like stochastic gradient descent with momentum. So to accelerate the convergence by incorporating information from previous gradient, helping smooth out oscillations. Which of the following is the adaptive learning rate optimization algorithm that combines the concept of momentum and RMS props? So obviously, Adam. How does early stopping help in optimizing deep learning models? So obviously, this by stopping when the validation loss starts, immediately we can stop when validation loss starts to increase the preventing overfitting. Which type of learning rate scheduling type typically involves reducing the learning rate by fixed factor after predetermined number of epochs? Obviously, step step decay. Step decay is the correct answer. So why batch normalization consider an important optimization technique in deep learning? So obviously in it is normalized in input, each layer stabilizing the learning process and allowing for higher learning rate. So next, batch gradient descent is faster than. So which is the main difference between the batch gradient descent or stochastic gradient descent? BGD or SGD. So what is the difference? So difference is batch gradient descent updates the weight after processing the entire data set, while SDG updates each single training examples. Ant theory we have discussed just now. So this is the mechanism. We have discussed about foraging behavior real ants. So it is used to find the optimal path in the graph, and the same concept we are using in the tiger graph as well. This is another database, graph based database. There also we use the same. So particularly the problem that can reduce the finding the good path through this state, which is traveling. This problem is implementation of salesman traveling problem. We study in the data structure. So how the ant colony works. So this is already we have discussed. So thank you for now.
Dr. Tarakeshwar Barwa, your explanation is very good.
Thank you so much, sir, for appreciation.
Yeah, and you have explained so many optimization techniques with the parameters. That's a great thing. And I understood each and everything, sir. Thanks for a nice explanation with the practical session. I think over to participants. You have any doubts, you can ask him.
So, good evening, sir. So, good evening, sir.
Good evening, madam. Tell me.
Sir, thank you for your clear and informative session, sir. And this session has given us a strong foundation about the various optimization techniques. Here, I'm having a very small doubt, sir. In this session, you were discussing about the list of optimization methods. In the later part of the session, you also discussed about the bio-inspired optimization algorithms too. And we all know in the recent years, this bio-inspired optimization algorithm is creating a boom in this deep learning models. So can you please suggest which one to choose? Whether we have to start with the optimization methods or directly we can choose the bio-inspired optimization algorithm. Is there any difference?
Yes, bio-optimized algorithm swarm optimization is the best approach because I have
Okay, sir.
find personally this is performing well. Even it is performing well. We have a small amount of data set or large amount of data set. Both data set is performing well. Even it
Okay,
is
sir.
required less amount of computation. Even
Mm.
if you have a without this can be run on without GPU. Only CPU is capable enough to execute this.
Okay, sir. Okay, okay.
If you
Hello.
face any further difficulties, you can ask me anytime.
Sure, sir. Thank you, sir. Thank you, sir.
Thank you. Any other question, participants? Dear participants, any other questions? So can we call it a day? Or if any questions are there, please feel free to ask me. I'm going to share this code with you. You can execute. I have shared this code. You may participants can execute and they can, and slide also shared.
Nice session, Professor.
Thank you. Thank you so
Thank
much
you.
for
Thank you,
your
Professor.
application.
Yeah.
Participants, any other question if you have?
Sir, myself, Dr. Manoj Bis, sir.
Yes.
Sir, my question is, sir, ki why excellent you discuss about optimization, the deep learning. It is wherever while working the different working machine learning and the deep learning, so some problems arise. So please, sir, your mail ID या telephonic mobile number, mention your presentation, sir. If you give you some mobile number या mail ID, then
Yes, sure.
yeah, yes, sir. Please, sir.
I will share on the chat. You
Yes,
can,
sir. Thank you, sir.
all right.
Thank you,
Any other
thank you,
question?
thank you, sir.
Any other question, participants? Thank you. Thank you so much.
Is there any other queries from the participant to be clarified by our chief guest?
Any other queries, participants?
Is there any queries from the participant to be clarified by our chief guest?
Dear participants, if any queries, questions,
Sir, shall we conclude this session?
yes, thank you. Thank you for giving me this wonderful opportunity. Thank you.
Thank you,
Thank
sir.
you, participants.
Thank you so much.
Thank you, sir.
Thank you.
Good evening, everyone. As we come to the end of today's insightful session on deep learning technique optimization, it is my privilege to deliver the vote of thanks. First and foremost, I would like to express our heartfelt gratitude to our esteemed resource person, Dr. Turkish Sir, for taking the time to share his valuable knowledge and expertise with us. This session was both enlightening and inspiring, giving us a deeper understanding of an important area in artificial intelligence. A special thanks to our chief guest for his gracious presence and for setting the tone for today's program. We would also like to extend our sincere appreciation to the Internal Quality Assurance Cell and the School of Computing of VET's Institute of Arts and Science for organizing this FDP and providing such a wonderful platform for learning and collaboration. A big thank you to all the participants for your enthusiastic involvement and attention throughout this session. Let us carry forward the insights we have gained today and continue our journey of learning and growth. Once again, thank you all. We look forward to seeing you in the upcoming sessions of this FDP.